So let's think about how we can classify single and double and triple bonds, which is what we're really used to dealing with, in terms of these sigma bonds and these pi bonds. So if we take a look at what a single bond is, and let me grab some molecules here. If we're talking about a single bond, we're talking about two orbitals overlapping in the internuclear axis. So if we have a single bond here, would you consider that a sigma bond or a pi bond? Right, it's a sigma bond. Essentially what we're seeing is overlapping in this z-axis here. In contrast, if we talk about a double bond, what we're now talking about is having both a sigma bond and also one pi bond. And I apologize, I intended to set this up right before class, but that didn't happen today. So, all right, so what we see here is we have our sigma bond. That's along the internuclear axis here. But we also have a pi bond because each of these atoms now have electrons in a p orbital. So we're going to have overlap of electron density above and below the bond. So that's exactly what our definition of a pi bond is. So we have one sigma bond and one pi bond. So now let's think about a triple bond. A triple bond, again, is going to have one sigma bond on the internuclear axis. How many pi bonds would you expect? 2, great. So we're going to see 2 pi bonds. The first one will be above and below the bond axis is where we'll see the electron density. And the second will be perpendicular to that, so it will be a density in front of and behind the bond axis. So we can kind of flip it this way. This will be one pi bond. This will be another, interacting between these p orbitals. One thing that I want to mention that is really important is once you have double bonds, what happens between those two atoms in the molecule is they can no longer rotate in relation to each other. So you can think about why that is. When we have just a single bond in a molecule, you have all the free rotation you want. You can just spin it around. There's nothing keeping it in place. But once you have a double bond here, we have our pi bond as well as our sigma bond. So there's electron density above the molecule, or above the bond, and below the bond. So if I try to rotate my two atoms, you see that I have to break that pi bond because they need to be lined up so that the electron density can overlap. So in order to rotate a double bond, you have to actually break the pi bond. So essentially what you're doing is breaking the double bond. So really, you cannot ever rotate a double bond. It makes your molecule very rigid. This is incredibly important because if you picture having a double bond in a very large molecule, you could have all sorts of other atoms off this way and all sorts of other atoms off this way. And you can picture the shape would be very different if you have one conformation versus another conformation. So it's very important that the double bond locks it in a particular conformation. This completely could change if you were to flip from one to the other conformation, which can happen in chemical reactions. If you were to make that change, you would find that the molecule now has completely different biological and chemical properties. And so it's very important to be keeping in mind that anytime you see a double bond, you have a pi bond there, so you're not going to see any rotation around the bond axis.